First of all, I would like to thank Dr. Siraj sir for inviting me to interact with emerging research scholars in the field of chemistry. And definitely it is great opportunity for me also to interact with the students of immense knowledge. And this way, I can also share some of my experiences of Gaussian study with you. Dear participants and PhD research scholars, first of all, I would like to welcome you on this online platform through which we are going to understand some important concepts of density functional theory. As this topic is very vast and based on quantum mechanics, it is always difficult to understand the theory, the concepts behind the Gaussian software. So what I'm going to do, I will share some demonstrations so that you can understand the basic things related to the density functional theory. And through these demonstrations, definitely it will become easier to understand some important aspects of computational chemistry. So as all of you are researchers in the field of chemistry, already many of you aware with the computational techniques in the chemistry applications. So there are so many computational methods which we are using to study the chemical reactions, to study the drug discovery. Similar to all these computational software, Gaussian is one of the software which is widely used to understand many things in the chemistry. I would like to share some basic things related to the Gaussian software with you. So dear participants, this Gaussian software initially was launched in the year 1970 by John Pople and the research group at the Carnegie Mellon University. And initially it was called as Gaussian 70. So there are many versions of this software. The latest version of this software is Gaussian 16. And since its launch, many updations, many modifications in the software has taken place. So there are different type of theories involved in the Gaussian software. Basically, this density functional theory, which is the basis of Gaussian software, is based on electron density concept. Therefore, it is density functional theory. There are many important levels, theories, basis sets which we are going to study. As I told with you, the current version of this software is Gaussian 16 and previously there was Gaussian 9. Now this software is licensed by the Gaussian. If we need to analyze the compounds, analyze the molecules using the Gaussian software, we need to purchase the software. As to publish the research paper, to publish the data based on Gaussian, we must have the licensed version of this software. Without this, we cannot go further. Dear participants, let me share with you some important applications of Gaussian software which you will study in these two sessions. So as I discussed with you, it is one of the important computational software and it is used to study the energies of the molecules, molecular structures, various types of spectral properties such as UV, NMR, IR, Raman, and it will give you many chemical properties, reaction descriptors, which I am going to share with you. So you can study the rate of reactions, you can study the reaction mechanism, you can study these transition states, you can study the intermediates using the Gaussian, even for inorganic complexes, metal complexes, for nanomaterial, you can apply the technique of Gaussian to study many important aspects. You can study the various types of energies, enthalpies, to understand the physico-chemical properties, thermodynamics of reactions. And as I discussed with you, spectral properties you can easily elucidate by using the Gaussian software. So this is the some basic things which I wanted to share with you. Let me share one thing so that you can understand all basic concepts related to today's session. So dear participants, I think my screen is clearly visible to everyone.
Yes, sir.
If there is any problem regarding the visualization, please let me know. I think the Gauss wave window is visible to everyone. Am I right?
Yes, sir.
Okay. Try to interact with me in this online lecture so that we can have appropriate discussion on this. I would like to know about the any research scholar here who is already having publication on Gaussian. Is there any research scholar who is having publication through density functional theory? Am I audible, dear students?
Yes, sir.
Is there any student who is having research publication or prerequisite of this Gaussian?
No,
No,
sir.
sir.
Okay. So on that basis, I will share the basic things also. Okay. So I think the window is clearly visible to everyone. So there are two main important things regarding the interface of Gaussian software. So as I told you, this is the license copy which I am having in my laptop. So I'm not going to discuss how it is downloaded, how you will get the crack version, as this is not ethical. So I'm only going to share the details regarding the software which already I am having. So this is the interface of Gauss view. That is the visualization application of Gaussian. This is the first window. And when you will open this, so along with this, so what you will get? You will get this type of window. So here, the second window which you all are able to see is the window to draw these structures. So already all of you are having knowledge of ChemDraw. So based on the knowledge of ChemDraw, you can easily draw the structures. So first window is the Gauss view window. And second window is used to draw the structures. And as I think both these windows are clearly visible, you can easily operate the Gaussian. Okay, let me discuss the important things which are available in this. So everyone is able to see this first window. So I will maximize it so to understand all things. So at the left side, you can see the file option is given. Correct? And here you can open various types of files in the Gaussian. Let me open one file so that you can understand what kind of files you can open. So dear research scholars, so here you can see the option. So various types of options are given. I think you are able to see the Gaussian input file, Gaussian output file, Gaussian formatted checkpoint file, Gaussian checkpoint file. I will discuss everything about these files. All these files are generated by the Gaussians. Then there is cube file, PDB file, MDL file, that is mole file, mole2 file, any crystallographic file, that is CIF file. So that is also available here. So such a type of files can also be opened in the Gaussian. And you can also select all files. So here, so different files are already available as I have run one Gaussian job in this. So you can see there is Gaussian checkpoint file, then Gaussian input file, there is text document, that is log file. I will discuss that log file also. And there is mole file which I have generated. Okay. So you will be able to see all these files when you will click on open option and you will go to the folder where you have saved the data. Correct? Then there is edit, view option, calculate, results, windows. All these are applicable when you will run the job. Okay. Now, below to this, you are able to see there is carbon written, and here there is benzene fragment which is shown, and different types of fragments are also shown here. Okay, let me show all types of things which are available here. So this is the blue window which you are able to see is used to draw the structure. So let me show how you will draw the structure to run the Gaussian job. So let me show you. When you will click the carbon, you will be able to see the periodic table and various types of elements which are there in the periodic table. So I am getting this only by clicking the carbon. So dear research student, are you able to understand how I can open the periodic table showing elements?
Yes, sir.
Yes, okay, thank you.
Yes,
Now,
sir.
when you will click the benzene, so you will get only benzene structure, and next to it is a fragment which is written by R. When you will click R, so you will get the fragment and various types of groups which we will need to draw. Correct? So you can see here, there is a nitro group, amide group, then there is carboxylic acid, a carbonyl, nitrile group. Many groups are there, and all these groups you can also build in this blue window. So all these options are available to draw the structure. So first of all, we will understand how to draw the structure in the Gaussian. We will go step by step so that you can analyze everything through the Gaussian. Okay? So let me draw one structure. Can you tell me any structure, name of any compound, so that we can draw in this interface?
Benzoic acid.
Okay. So if we need to draw the benzoic acid, so what you have to do, first of all, as I told you, so different types of elements, fragments are already there. So I will click the benzene, and by clicking the benzene, only what you have to do, you have to click in this window, that is blue window which is shown here, and you will get the structure of benzene in this window. Why we are drawing the structure? We are drawing the structure to understand different properties of particular compound. As one of the students said, the name of benzoic acid. The benzoic acid, different properties of benzoic acid, chemical, electronic, can be predicted by running the job in the Gaussian. So we need to draw the structure of benzoic acid. So here you are able to see the benzoic acid. Next part is we need to attach the carboxylic acid group. So I think you are able to see the structure, and in this structure, see all carbon atoms, 6 carbon atoms and 6 hydrogen atoms are shown. To any carbon atom, we can attach the structure of carboxylic acid group. Am I right? So what you have to do, either you select the carboxylic acid group from the fragment. So here next to that interface of benzene, different groups are given. So here, are you able to see the carboxylic acid functional group?
Yes, sir. Yes.
Yes, absolutely. Okay. So by clicking that carboxylic acid here, now you have to attach this group to one of the carbon, correct? One of the carbon of benzoic acid. So you need to select one of the hydrogen, as we are going to replace hydrogen by a carboxylic acid. So I am selecting any hydrogen from any one hydrogen from this structure. So if you click randomly, so you will get structure like this. This is not correct. So you need to select at least one hydrogen, as we need to replace the hydrogen by the carboxylic acid. So we will delete this one. So only you have to do Control Z. Already you are knowing how you know how to operate the laptop. Okay. So I will click here. So one of the hydrogen is replaced by carboxylic acid. Are you able to see, dear students? So this is structure
Yes, sir.
of carboxylic acid. So first part
Yes, sir.
to understand the working of Gaussian, we must know how to draw the structure, correct? Now, this structure can be visualized by rotating the structure, by operating through the mouse. So you are able to see, you can see. So any direction can be visualized. Okay. So this is the structure. Now, if there is any deviation in the bond angle, so what you have to do, you have to clear this structure. You have to rectify this structure by using the brush. Dear participants, are you able to see the brush symbol?
Yes, sir.
Okay.
Yes, sir.
By clicking it, so you might have seen the slight change in the structure. So until you get the final outcome, you can click on the brush and you will get the structure. You will get the structure of the molecule for which you have to perform the analysis. Correct? So this is the first part of this software. Okay. Now you might have understood the basic thing related to the structure drawing in the Gaussian. Sometimes what happens, students are not able to, research scholars are not able to draw the structure in this window. So what you can do, you can generate mole files in the ChemDraw software. So I will open the ChemDraw interface. Is it visible to everyone?
Yes, sir.
And I think all of you are appropriately handling the ChemDraw version. So there is no problem regarding the operating of ChemDraw software. No student is having problem regarding ChemDraw. So I will show you how to generate the mole file. Let me draw the structure of benzoic acid in this. So as all of you are PhD scholars, so already you are having knowledge of ChemDraw software. Okay. I can provide you ChemDraw software. I have that copy of ChemDraw, but I cannot provide you Gaussian as it is not ethical. But if you need ChemDraw software, I have the ChemDraw software. I am also having the software to draw the NMR. I will share with the Siraj sir, so you can get it. Okay. So this is the structure of benzoic acid, which I have drawn in the ChemDraw software. So by clicking on the file option, so you can save the file, that is save as. So I have made one folder here as a chalcone. So here I will save the structure of benzoic acid as benzoic acid. Let me save it. Okay. So here you are able to see different types of versions are available. Different types of file types are available. Correct? Dear research scholars, are you able to see different types of file types?
Yes, sir. Yes, sir.
Yes, sir.
So here ChemDraw, XML, ChemDraw 3x, different types are file types are there. So we need to save the file type as mole file. Are you able to see the mole file? Mole
Yes,
type?
sir. Yes, sir.
Okay. So I have clicked on that and I will save the file as benzoic acid mole file. Okay. So if you are not able to draw the structures in this interface, simply draw the structure in the ChemDraw. Sometimes what happens, dear research scholars, it becomes very difficult to draw the structure in this interface of Gaussian. So what we have to do, we need to draw the structure in the ChemDraw and save it as a mole file. Then we will click on this file option. Then on open button. So we will go to the folder where we have saved the file. I think everyone is able to see the mole file of benzoic acid. I will click on that. And simply you have to click the option open. So are you able to see the benzoic acid?
Yes, sir.
Yes, sir.
Okay. But I think the radius of atom is large, the diameter is large. So what we will do, what you have to do, you have to click on which button, which option?
Brush.
Brush. Yes, I will click on brush option. And I think you are able to see the structure of benzoic acid in the Gaussian window. Right? So, dear research scholars, in the field of your research, if you doing the calculations using Gaussian. So first part is to draw the structure using the Gaussian. Okay. Now we can run the job. We can predict many properties of molecule through the Gaussian. Let me share with you some of the research papers so that we can understand what kind of properties we can generate through Gaussian and how they are important for the research study. Okay. Let me share with you one of my research paper and what kind of properties we have determined using the Gaussian software. So dear research scholars, are you able to see this research paper? That is reactive sensing of gold by coumarin tethered fluorescent probe through alkyne activation. What we did in this research, so we synthesized one compound and that was used as a fluorescent probe. This is one of the research study for the sensing of gold. And for this, let me show you what kind of properties we determined. Okay. So everyone is able to see. First thing, through the Gaussian, we get the lowest energy structure, the structure of a compound with minimum energy. And this can be obtained through the Gaussian. The minimum energy conformation, minimum energy structure can be obtained through the Gaussian. So the interface which you are seeing here, so it is the optimized structure. So such a type of optimized structure can be obtained. I will tell you importance of this also. And I think you are able to see this part of study also. Can anyone from you recognize this? What is given in this image? No one? Okay.
Molecular orbitals.
Yes, frontier molecular orbitals are shown. Dear participants, what is shown? For frontier molecular orbitals. Frontier molecular orbitals are HOMO, that is highest occupied molecular orbital, and LUMO, that is lowest unoccupied molecular orbital. And we know that understanding of HOMO and LUMO is very important in many parts of chemistry. And this was also important when we study the gold sensing through coumarin probe. So for this study, we needed the HOMO-LUMO understanding. So we determined the HOMO-LUMO energies. Along with this, we have determined the band gap energy between the frontier molecular orbital, that is HOMO and LUMO. So all these properties are determined using Gaussian. So you can get the stable structure, stable conformation from the Gaussian. Then you can elucidate the HOMO-LUMO, that is frontier molecular orbital. And through this, you can determine many important properties, so which we will study here. Correct? So this is one of our paper. Another research paper of one of my student. I was not part of this study, but I would like to share what kind of study he has done. So dear students, are you able to read the title of the research paper?
Yes, sir.
It is some kind of organic light emitting diodes have been prepared by using the triazolopyridine hybrids as a host material, and for these organic LEDs, understanding of optimized molecular structure, which I discussed with you, understanding of HOMO-LUMO, understanding of U visible spectra. So I think you are able to see here, this is the absorption spectra, that is U visible spectra, which is determined using Gaussian. Then I would like to show you this one. That is, again, you are able to see the HOMO-LUMO pictures of these compounds, correct? So for this organic LED applications, again, use of this Gaussian software is very important, correct? And many different properties have been determined. So this table 2, which is very important part of this study, is determined using Gaussian study. Okay, this is another study. Let me share with you another research article from our research group, this one. I think everyone is able to see, correct? So this is fully based on the Gaussian study. Less part is from the synthetic chemistry. Okay. So I think all of you are able to see. So these are the different conformations of the compound which is studied in this. This is the compound number 3, which is a oxidizole compound. And through the Gaussian, so you can see number of structures we determined, and out of this we arrive at 2 structures in which minimum energy is present, correct? And this is possible, this we can determine using the Gaussian software only. So here the most stable structures are presented, and here I think everyone is able to see the table number 1. This table number 1, that is different bond lengths of the synthesized compounds are shown here. Similarly, we can determine the bond angles. Along with this, we can determine the dihedral bond angles also. So all these properties we can determine by using the Gaussian software. So here again, we have shown the HOMO-LUMO pictures. Okay. Now, dear participants, are you able to see this image here?
Yes, sir.
So what I discussed with you, I have discussed with you the minimum energy structure, that is optimized molecular structure, which we can obtain from the Gaussian. Then we can derive the HOMO-LUMO energy levels, HOMO-LUMO pictures, that is frontier molecular orbitals. And this is also one of the important aspects we can get from the Gaussian. This is molecular electrostatic surface potential plot, which is in short is called as MESP or MEP, molecular electrostatic surface potential. We will discuss what is this, how it is important, and what is exactly different surfaces shown here. It is molecular electrostatic surface potential, and this one is the contour plot, and that contour plot is similar to the MESP. Okay. And this table number 5, that is Mulliken atomic charges of various atoms present in the structure, can also be predicted. So everything shown here. Then this is the theoretical spectrum, IR spectrum, which is obtained using the Gaussian software. So everything about the physical and chemical aspects obtained from the Gaussian. Okay. Okay. Let me go to the main part of this software. I think we are back to the interface of Gaussian software, correct? Dear students, are you able to see this one?
Yes, sir.
Okay. Now, I would like to show you another important thing which we can use in the Gaussian software. For structure building, if you right click on the Gauss View window, then you will get this type of option. And I think you are able to see in this interface. So what is shown? First thing, that is builder, correct? In this builder, several options are given by which you can modify the bond, modify the angle, modify the dihedral angle. You can add the valence. For this, that is add valence, you can extend the chain of any compound by using this option. Let me click on this add valence so that you can understand. Let's see here at the ortho position of this compound, you are adding some groups. Okay. Let me click on this left side, that is periodic table option. And here you are taking the nitrogen. You are adding the nitrogen here at this point, ortho position. Okay. So you are getting the NH2 group here. Now, if you need to add hydrogen at this nitrogen, so what I shown to you, simply click on the builder and you can select the add valence. So here you can see and hydrogen is added. And by clicking on this hydrogen, you can extend the chain. Okay. So this is one of the options which is available here. So we will go back to the benzoic acid. Now, let us understand what kind of jobs can be performed using the Gaussian. So I will be discussing with you optimization, that is how to gauge the lowest energy structure using the Gaussian. Then I will be discussing with you the energy calculations, frequency calculations, and NMR calculations. 4 important things we will discuss in 2 sessions. First, optimization. Second, energy calculations. Third, frequency calculation. And fourth one is NMR calculation. Other than this, there are many things you can predict. But for these 2 sessions, I will limit my discussion to only these 4 important things. Okay. So first part, to study the properties using Gaussian, we need to optimize the structure. Optimize means to get the structure with lowest energy. Now to get this structure, what you have to do? So you have to click on this calculate button, calculate option. I think everyone is able to see this thing. Okay. Now when you will click on that calculate option, so only you have to click on the first thing, that is Gaussian calculation setup. I think everyone is able to see. And when you will click on this Gaussian calculation setup, you will get this type of interface. Let me maximize it so that everyone will be able to see it. Okay. I think The interface is clearly visible to everyone. So are you able to read what is shown there, dear participants?
Yes, sir.
Okay.
Sir.
What is given to the left part? This one first.
Job type.
Yes,
Type.
absolutely. Yes. Yeah, very good. It is job type. And I think you are able to see here energy, optimization, frequency, optimization plus frequency, IRC, scan, stability, NMR. Many options are shown there. We are going to discuss optimization, we are going to discuss energy, we are going to discuss frequency, and also NMR. These four parts I'm going to cover. So what I discussed with you earlier, we need to optimize the structure. We need to get the stable structure of particular compound to understand its properties. Correct? So first task will be to select the optimization type. So job type must be optimization. Correct? So here options are given: optimize to TS Berry, optimization to minimum. So we have to select this one, that is minimum. And then we have to click on method. So everyone is able to see what is shown in the method.
Yes, sir.
Okay. So you can see here options are there, ground state and other different options are available. As we are focusing on the ground state, minimum energy level, minimum energy state, I will click on ground state. Correct? And in the next part, different types of levels are given. So dear participants, I would like to share with you one of the important thing regarding this application. So this is important part of this software. Many levels are available. So you can see the mechanics is there, semi-empirical is there, RTFOC, DFT, MP2, MP4, CCSD, many things are there. As earlier I discussed with you, I told you I'm interested in density functional theory, applications of density. I will click on DFT method. So when you will click on density functional theory, which is based on electron density of molecules and determine many important aspects on the quantum, based on the quantum chemistry, utilizes electron density models. So here we have to select DFT. Then here again you will see different options, number of options. Here you have to choose the default spin. And here in this case, so we have selected a DFT method. Which job type we are doing? We are doing the optimization. Then we have here the last part is called as functional. Various functionals are there in the density functional theory. Based on the molecules which we are studying, with appropriate literature survey, we have to choose a particular basis set.
Hello. हाँ बाबू पूछो.
So here, generally used basis set, you will see in most of the research paper, in most of the study, is B3-LIP. What is B3-LIP? B3-LIP stands for Becquet 3-parameter Li-Yang par level. Again, I am repeating. It is Becquet 3-parameter Li-Yang par system. Okay. What is the full form? It is not important. It is called as functional. B3 leap is a functional which is used in the density functional theory. After that, you can see basis set is given. Again, I'm repeating, what kind of functional you have to use depends upon the molecule which you are studying. You cannot use same functional for all types of molecules or different types of molecules. So based on your study, you have to choose the appropriate functional. Then you can see here, so basis set is given. So starting from STO3G, various basis sets are there. STO3G, 321G, 631G, 6311G, then CCP-VDJ. Different types of basis sets are given. So you can select the appropriate basis set based on your study, what kind of study you are doing. So let me select this basis set, 631G. So new window will appear, and here the two important signs are there, whether you have to perform with 1 plus sign, 2 plus sign. Again, this depends upon what kind of study you want, whether your calculations will match with your experimental data or not. Then the diffuse parameter is given, D, 2D, 3D, DF, 2DF. So again, here, whether to select D or not depends upon the molecule, depends upon the study you are doing. Then there is polarization function, P, 2P, 3P, like that. So here, let me select here P. Only I am showing how it operates, okay? Then here, as this compound, this molecule is neutral, charge is 0, and it is present in singlet state, okay? So different types of functional are available, different types of basis sets are available, different types of diffuse functions are available, polarization functions are available, and based on your study, you can select appropriate one. So this is very important part in your calculation. Then comes your title. You can give appropriate job title. If you are doing the optimization, you can give the optimization name like this, optimization, and it is benzoic acid like this, as per your convenience. And then there is link 0, nothing to do with this. You can increase the memory size, but here we will not discuss this. Then there is another important things, NBO, that is natural bond order analysis, but we are not interested in this, so we will keep this as a none. But in many study you will see the NBO calculations. And next part is solvation. So if you want to do calculations, one important thing which I forget to tell you, this Gaussian study operates in gaseous phase and not in solid phase. This is the limitation of this technique. So all calculations will be done in the gas phase. If you need calculations in any of the solvent, only you have to click on this solvation part, that is default, and you can select the solvent, different solvents which they have provided. So if you need to do the calculation in the solvent phase, you can perform the calculation in the solvent phase. For U visible study, we know that we record the U visible study, U visible spectrum in different kinds of solvents. So here choice of solvent is very important when it is U visible study. So here I am selecting default. I am selecting none. That is, this calculations will be done in the gaseous phase. So I will repeat all the parts again. So as I need the optimization study of benzoic acid, what I have clicked here, only optimization, different options are available. Method I selected DFT method, ground state, B3 leaf functional, a basis set is selected, and in the solvation, no solvent is selected. That is, calculations will be performed in the gaseous phase. Charge is 0 as this is neutral compound. Correct? So with this, you can run the Gaussian. So for that, you have to click on the submit option, which is shown at the bottom. So when you will click on the submit, now I will select lower basis set. What is important thing? Higher level will require long time to run the Gaussian job. With the computer system such as i5 system, i7, 64-bit, high memory, high GB, high RAM. Even with this, sometimes it requires days, 2 days, 1 day. For this, we require supercomputers. But with the system available in our laboratory, usually with higher basis set, higher functional, sometimes it requires 2 to 3 days also. So what I will do, to show you the calculations, I will select a simplest basis set, so that calculations will be performed within short period of time. So I have selected STO3G, and only then you have to click on the submit button. So it will ask to save the file in appropriate folder. So I will click on the save button. So it has opened one folder. So I will save this as a optimization file of a benzoic acid, and then you have to click on save button. It will ask submit the file to the Gaussian. You have to click on OK. So are you able to see the Gaussian job is running?
Yes, sir.
Okay. So
Yes.
let this job run. I will show you the calculations which already I have performed. Okay. I will open. After job is completed, you will see a window here that I will show how it is shown. So what I will do, I will show you the job which is already performed by me. So for that, you have to click on this option that is open. And so as I discussed with you, so many options are available to analyze the file. So you have to click on Gaussian output file, which is also called as log file. So are you able to see this option? That is Gaussian output file, that is log file.
Yes, sir.
Okay. So after clicking on this Gaussian output file, are you able to see a log file named as Chalcone? Dear participants.
Yes.
Yes,
So
sir.
what I will do, I will click on this Chalcone. This output file is generated when Gaussian job is completed. Okay. I will click on this open button, and I think you are able to see the optimized structure. Correct? Are you able to see the structure?
Yes, sir.
Yes.
Yes, sir.
Okay. I think you are able to see the structure. So this is the structure of chalcone compound, which is having a nitro-methoxy group, a nitro group and methoxy group, which I optimized this morning to show you. Okay. Are you able to see this window? That is Gaussian job has completed. Do you want to close the window?
Yes,
Yes, sir.
Means the optimization of benzoic acid is completed with the basis set. As I selected low level of theory, it is completed within few seconds. So I will close this. So it is already saved in that folder. Okay. So here, what I have opened one compound optimized file. So how you will analyze this optimized file? So there are number of options available. If you click here on this view button, here to the Gauss view interface, you can also click. So there is a display format option available. I think everyone is able to see. When you will click on this display option, you will get a new interface in which many options are available. So let us understand what kind of things can be done with this optimized structure obtained using Gaussian. So here I think everyone is able to see this background color, which is blue now. Correct? So if you click and if you want to change the background color, you can easily change and make the color which you need. So I have taken here white as a background color. Then by clicking on show labels, what you will see the atomic numbering in this compound as per Gaussian. But I think you are not able to see the number due to its smaller size. For that, you have to click on this text option, increase the size of the number, and I think you are now able to see the atom numbering, correct? Why it is important? When you will derive the charges, when you will try to interpret many other things, this atom numbering is very important. So I have shown the atom numbering here, correct? And here, when you will click on the molecule option, you can visualize this molecule by number of ways. So here first option you can see which option is shown, ball and bond type of option is shown. You can select the ball and stick model. So you can see the structure has changed now to ball and stick model. Similarly, you can go for tube model if you need. What kind of representations you need, based on this, you can select the representation. You can go for wireframe option. Such a type of representations can also be used. So let me go to the ball and bond type. So this is the ball and bond type of representation. So I have changed the atom numbering size. I have shown you various types of representations. You can also here show the symbols. But as we can easily recognize with the atoms, which atoms are there without symbol, need not to show the symbol. So here, in this way, we have viewed the optimized file in the Gauss view, correct? Now, you need to save, if you need to save this file, only you have to click here on the file button. By clicking here the file option, you can save the file, that is save image file. So by clicking on this, you can save this file as optimized file of this compound in appropriate folder. Okay. Now, this is not the only thing we have obtained through optimization. So when you perform the optimization, you get many different properties of the molecule. So when you will click on the result option, so here on the left side of the Gauss view, I think everyone is able to see the result option, correct? And when you will click on the summary, so what kind of properties are you are able to see? Can you tell me, dear participants, what kind of properties are shown as a result summary?
Dipole moment.
So here you can see the dipole moment of this molecule in the gas phase, that is 6.71. Point group of this compound is shown, that is C1 point group, and the EB3 leap energy which we have calculated, which is shown here, that is minus 961.79 atomic unit. You can convert this value into appropriate unit by using appropriate physical chemistry calculations. What kind of units are needed, that I will also discuss with you. And the charge on the molecule, already we know it is neutral, so charge is 0. The basis set which we used for this calculation, and the calculation type is optimization. We have performed the optimization. So by viewing the result summary, you will see dipole moment, the job type, the energy of the molecule, point group, charge on the molecule, everything you will see. Okay. You can save this data by clicking on the save data. So this is the first part you get through the optimization. Now, if you right click on this structure, what you are able to see. What options are shown there? Can you tell me?
Builder, file, edit, link.
Builder option is there, file option is there, edit option is there, view option is there, calculate. We don't need calculation now, so need not to do calculations. Results. Now, in the results, what I have shown you, a summary of the results. Am I right? Now,
Yes, sir.
you can view the result file. So if you are able to see the view option, view file at the bottom. Are you able to see the view file option?
Yes, sir.
Okay. If you click on this view file option, so you will get a text file, WordPad text file in the WordPad. Are you able to see, dear participants?
Yes, sir.
Okay. So now, so many calculations, so many data are shown in this file. The data which I will discuss with you, the important thing which I wanted to discuss with you is bond length and bond angle parameters of this compound. So by analyzing the view file, you can get the information about the bond length and bond angle. So for that, so you have huge data here. For that, what you have to do, only you have to click on find option. So what I will write, I will click on optimized, because we need optimized bond length, bond angle. Here, so many values are given. You will not able to get the optimized parameters. So only I will click on optimized, find optimized. By clicking this, I think everyone is able to see we have arrived at the optimized parameters. Dear participants, are you able to see?
Yes, sir.
Okay. So if you need the bond length parameters of the compound, bond length, bond angle, dihedral angle, all these parameters can be found here. So here the atom number 1, atom number 2, and its bond length in angstrom is shown, that is 1.3853. So which is atom number 1 and 2? You can see in this structure, the atom number 1 and 2 is this one, 1 and 2. Correct? Its bond length, you can see here. So you have to make a table of bond length. I've shown you one of my research paper in which we reported the bond length of one of the compound. Correct? So various bond lengths you will find here. Correct? Similar to this. So after the bond length, I think here all of you are able to see the angles. Correct? Angle between, first angle is shown as A1 216. Its angle is shown in front of it. After this, you will see the dihedral bond angle. So here, dihedral bond angle starts from D1. So by knowing the result file, you can get the information about the bond length, you can get the information about the bond angle, you can get the information about the dihedral angle. So what we have obtained by optimization? We have obtained the optimized molecular geometry, its dipole moment, its energy, its point group, bond length, bond angle, dihedral angle. Another important thing here you will get is Mulliken charges. The charge present on the particular atom. So here, when you will click on Mulliken, you will see, so there are 34 atoms in this compound, correct? And you will be able to see the charge, Mulliken atomic charge on a particular atom. So from this you can determine out of various atoms, which atom is having most positive charge, most negative charge. Out of various carbon atom, which is having most electronegative charge, most electropositive charge in terms of Mulliken atomic charge. So this data is also shown here in this output file. So let me go to the structure. So by doing the calculation, what we have obtained? Again, I'm telling you, we have obtained the stable structure, its energy, bond length, bond angle, dipole moment, dihedral angle, Mulliken atomic charges. Correct? So all these, whenever you will need all these properties, so you can get it from the Gaussian software. This is one thing regarding the output file. Okay. Now, dear participants, let me show you another calculation. So this was the optimization calculation. If anyone is having any query regarding the optimization of molecule through the Gaussian, can ask me if you are having any doubt. Is there any student who is having, or research scholar having?
Sir, can we do DFT for some inorganic compound?
Yes. For inorganic complexes, you can do the calculations. For nanomaterials, you can do the calculations. This is...
Sir, I kindly request you to please explore some simple inorganic compound. How
yes,
to
we can
calculate this?
Same way. What you have to do again? What you have to do? You have to run the job. You have to draw the structure in the ChemDraw, and that file you have to extract here in the Gaussian. As I told you, it take time. So you can, if you are having Gaussian, or any of your colleague is having Gaussian, what you have to do? Only you have to draw the structure in the ChemDraw, save it, the file as a mole file, extract here in the Gaussian and run the job. Only thing what you have to do, by using appropriate literature, you have to select the appropriate basis set. Whether you have to select the diffuse function, you have to select the polarization function, the type of functional which you need, that we have to select on the basis of the type of the inorganic complex. Whether we need D, whether we need F function, that is very important. And this simply you can do by using appropriate literature. For inorganic complexes, you can do. For metal complex, what I am saying, nanomaterials, you can also do.
Thank you.
Another thing, any student would like to ask? Okay. If everything is understood, let me share you another calculation which you can perform using the DFT. So first we have performed the optimization calculations. Now, if you need the HOMO-LUMO energies, what you have to do? You have to perform the energy calculations. If you need the U visible spectrum, again you need the energy calculations. So what you have to do? To perform any other calculations, you have to take the file which you have optimized, correct? So we have optimized two files. This morning I optimized a chalcone, then I have shown you the optimization of benzoic acid, correct? What I will select here, again you have to see what kind of options are available. I have selected the output file. You have to select the molecule which you have optimized. So I will select a chalcone molecule which I have optimized. You have to open it in the Gauss view. Okay. Now, this is the optimized structure. Now I need to perform the energy calculations for determining the HOMO, LUMO, that is frontier molecular orbitals. For U visible spectroscopy analysis, again I will go to the calculate option. So here in this window, here again it is available. I will go to the Gaussian calculation setup. Again you will be able to see the same window in which various types of basis set functional job type is given. Okay. So what we are doing now, we are performing which calculation? Energy calculations. Why we are performing energy calculations? We are performing energy calculation to determine the frontier molecular orbitals, to determine the U visible spectroscopy, to determine the absorption spectrum, to determine the excitation energies. Everything I will show in this job. So here, are you able to see the energy?
Yes, sir.
Okay. So only you have to click on the energy option. Then you have to click on the method. Okay. So now the method, here you have to select. It should be TD method. Which method you have to select? Again, I am repeating. It should be TD. TD is time dependent theory. Time dependent level you have to select. And again, here next you have to select the DFT and appropriate basis set. And here what is shown at the bottom. So here what options are available for you? They have given solve for more states. Now, for different type of studies, you need calculations for different excited states. Excited state 1, excited state 2, excited state 2, 3, 4, 5, like this. So here, number of excited states can be selected. So here 6 option is given. You can select 1, you can select 2. Again, this depends upon what kind of study you need. Let me select 2 excited states to show you. So here I have selected number of excited state 2. So here you have to select the DFT method, B3 I will not select higher basis set, higher level of theory, as it requires more time. Then, solvation is very important. If you are performing the energy calculations to get the U visible spectroscopy analysis, if you are performing the experimental work in a particular solvent, here you need to select a solvent by clicking on the default. Model is given default. Various models are given. Here to show you, I will select default. Solvent is given default. You can select water, DMSO, nitromethane, acetonitrile. Various solvents are shown there. So to make the thing simple, I will not select any solvent as it will require more time. So for job type, when you require the energy calculation, when you require the HOMO-LUMO energy calculations, when you will require the visible spectroscopy analysis, you have to select the job type as a energy. Method, time dependent method with DFT, TD-DFT method, B3 functional. Again, all these functionals basis set depends upon the type of molecule you are studying. Here I have taken the simplest level of theory to calculate the energy calculations. Okay, solvation which I have selected, none. Only you have to click on the submit option. Okay, let me show you, dear participants. So you have to save the file. So I will save the file as chalcone, and we are doing the energy calculations. So I have shown as a chalcone energy calculation. So are you able to see the Gaussian is running here? Energy calculations are running. I think everyone is able to see. Correct?
Yes, sir. Yes.
Okay. When the calculations will over, I will show you how to analyze the files which we have obtained. So first thing, today we have optimized the structure. I have shown you how to optimize the structure using the Gaussian software and what kind of results are obtained through this optimization. The second calculation which I discussed with you is for energy calculation. Through energy calculations, we can get the information about the we can get the information about the HOMO diagrams, LUMO diagrams, then about the visible spectroscopy and various excitation levels. Beside this, many things can also be obtained, but the basic things which we need, I am discussing with you. Let me show you one research paper till our job is completed. Dear participants, are you able to see this window of research paper?
Yes.
Okay.
Yes, sir.
So, to the left side, they have shown the absorption spectra, correct? So, we will get this absorption spectra through this energy calculations. Then, you are also able to see the table of absorption energies, oscillator strength, transitions, what kind of transitions are taking place. So everything is shown in this table. If you have understood, can you tell me which method they have used for DFT calculations? By looking at the table 2
B3,
description, can you tell me?
B3 LYP.
It is
B3
B3
LYP.
LYP, B3 lift, TD time dependent level, basis set is 631G DP level of theory, that is basis set, correct? And for the same optimized geometry, what they have shown here, this calculation is performed on this level of theory, for which geometries, the geometry which was optimized earlier by using same level of theory without time dependent function, that is B3 lift 631G DP optimized geometry. Now in this table you can see the transition taking place from, for the first compound they have shown S1 state, S2 state, S3 state. Calculation is done for 3 state. I have shown you can perform the calculation for the number of state which you require. In our calculation, we have performed the calculations for 2 states. Then the orbitals involved in the transition they have shown. The orbital number 95, 96, 95, 97, 95, 98. The transition is corresponding from which HOMO orbital? HOMO to LUMO orbital, HOMO to LUMO plus orbital plus 1, HOMO to LUMO plus 2 orbital, like this. So everything can be obtained through theoretical data done through the Gaussian. Okay. The job is still running. I think it will be completed within a minute. So this is the data which we will get through energy calculations. Then this type of pictures, that is HOMO and LUMO pictures, can be generated through Gaussian. Let me take the example which is already completed till our job is completed. Okay. Now, to visualize the files, the Gaussian energy files, and to get the information about the HOMO and LUMO pictures, again, what you have to do, you have to click on the file option, then you have to click on open button, correct? Here you need to check the, you need to take checkpoint file to draw the HOMO and LUMO pictures. You can take the output files, but again, you have to load checkpoint file. I will show you how you have to load the checkpoint file when you take the output file. But we will make the thing simple. So I will select the checkpoint file. Are you able to see the various checkpoint file?
Yes, sir.
Okay. So I will select a checkpoint file, and again you will see the optimized molecule, correct? Now, by double clicking here, you have to click on edit button. Edit option is given. Are you able to see the edit option?
Yes, sir.
Okay. By clicking on this edit, you will get a new interface in which MOs are given, molecular orbitals. By clicking on this molecular orbital, a new interface will open. Let me maximize it. Are you able to see?
Yes, sir.
Okay. You can see to the right hand side, different levels are given starting from the molecular orbital 1 to molecular orbital 215. Are you able to see here? In which the highlighted portion is nothing but frontier molecular orbitals. So the molecular orbital number 74, which is occupied by 2 electrons, is highest occupied molecular orbital, that is HOMO. And in front of HOMO, the molecular orbital 75 is lowest unoccupied molecular orbital, that is LUMO. So everyone is able to see. Can you tell me the energy values which are shown there?
Minus 0.32937.
Yes, minus 0.32937. This is given in AU atomic unit. Can you convert AU into electron volt? Is there any participant who knows how to convert? Because we need the values in electron volt, that is EV. So what we have to do for our further calculations, we need to convert this atomic unit value into electron volt. So any participant who is already knowing how to convert this value into electron volt? Okay. If you don't know, in tomorrow's session, you need to tell me. You can search anywhere through internet. You can search and tell me how to convert, how to transform this value into electron volt. You can take this screenshot of this value and you have to tell me its value, HOMO and LUMO values in electron volt. Okay. You can take this screenshot of these values and we will see what kind of other properties we can evaluate from these HOMO-LUMO energy values. Okay. Now, everyone is able to see the interface. What is given here below? You can see at the left corner, left bottom corner, visualize option is given. Correct? Dear participants, are you able to see this visualize option?
Yes, sir.
Okay.
Yes.
Here, when you click on visualize option, this part, when you will click, you will see the type of orbital picture you need here. So you can see here HOMO, LUMO, both HOMO, LUMO, this type of things are given. So I will click on HOMO. You will see here its number. It is 74, correct? And here also it is 74. After this, what you have to do? You have to click on update option. Are you able to see this update at the right corner? Right bottom corner?
Yes, sir.
When you will click on this update option, the HOMO picture will appear after certain time. Now you are able to see the HOMO picture. I think everyone is able to see, correct? HOMO picture,
Yes,
that
sir.
is highest occupied molecular orbital, has been generated by the Gaussian. So you can see in this HOMO picture, which part of the system is occupied by highest occupied molecular orbital, where that HOMO is distributed. You can see on the right part of the system, the HOMO is distributed. Correct? Now you can save this picture by clicking on the file option. By clicking here, your new window will appear, that is file, and you can click by clicking the save image file, and here you can save the HOMO picture of this compound, of this molecule. Now, if you want to change the background of this HOMO, you can click on view. Already we have discussed. You can go to the display format and change the background color to white or the background color which you need. So in this way, you can generate the HOMO picture, HOMO energy level, LUMO energy level. Now, if you want to generate the LUMO picture, again on the left corner of this, different orbital types are given. Only you have to click on LUMO, and after LUMO, where you will click? Can you tell me where you will click?
75.
Yes, 75 will come. You have to click on update. Update. And after certain time, the LUMO picture will appear. So you can see it is different from the HOMO, and you can easily recognize where LUMO distributed, on which part of the system LUMO distributed, correct? So here on the left part of the system, this LUMO is distributed. Again, you can click on the file, save image file, and save this as a LUMO picture of this compound. So in this way, you can determine the HOMO energy, LUMO energy, then you can derive the HOMO picture, LUMO picture. Now, I think our job is completed here. Gaussian job is completed. Let me show you this file. So I will close this window. So what I will do, I will click on file, open. So which file I will need? I will need output file because I need result. So here number of options are available: chalcone energy, chalcone optimization of benzoic acid. Which calculations we have performed? We have performed energy calculations. So I will select the energy file. I will open it. Now, when you will click on result option, what you will see? What you are able to see? Can you tell me when you click on result file of that output file of energy calculations?
Summary.
U visible spectrum and view file, correct?
Yes.
Okay. Now, due to time constraint, I will not show you view file. Rather, I will show you U visible spectrum. In tomorrow's session, we will see the remaining part. When you will click on U visible spectrum, I think you are able to see the U visible spectrum of this compound in the gas phase, correct? And you can see we have generated the U visible spectrum for two excitation energies, two levels. This is first. When I will click on this, you can see at the bottom, its wavelength is given as 378 nanometer with oscillator strength of 0.1464. And the second is also there. When I click here, you can see here it is 390.7. This is first, that is 390.79, and second is 378. And you can save this picture again by double clicking this. You can export the image, you can export the data, You can save the data and redraw in Origin or Excel software. That I will show you in tomorrow's session. So let me revise the things and then we will take questions if you have. So dear participants, what we have seen today, I have shown you how to operate the Gaussian software, how to perform the optimization through the Gaussian software, what kind of data is generated in the result file of optimization. Then we discuss how to perform the energy calculation through Gaussian, how to derive the HOMO and LUMO energy levels, HOMO-LUMO pictures. And then we also saw the visible spectrum for two excited states, two energy levels. And remaining part, that is molecular electrostatic potential surface plot, then how to use these HOMO-LUMO energies for further calculations, then different types of oscillator strengths, everything we will see tomorrow. Frequency calculations, Raman calculations, NMR calculations, all these parts will be covered in the tomorrow's session. I think I have tried to convey all this concept in the simplest manner. And if you need this kind of study in your research, you need this Gaussian software, license copy of this software. You can do the study by collaborating with other researchers also. But if you need, for this, you need to understand whether you need this kind of study in your research work or not. So now if anyone is having doubt related to this, we can take. If you are not having any doubt, we can transfer this session to the organizers. Siraj sir.
No, sir.
Hello, good evening, sir. Hello. Can you calculate the same thing for the charged molecules?
Yes, we can calculate for the charge molecules. What you have to do in the while optimizing the structure in the, if you are calculating for anions, then you have to give the minus charge while while doing the optimization calculation. If you are doing for cations, then you have to give that charge in the optimization. And there also you can get the importance about the type of state present, whether it is singlet, triplet, everything will be shown. You can perform the calculation for charge ions also.
Actually, I'm looking for the ionic liquids, which are the combination of cation and anions. There
Yes,
is no visual.
no problem. No, absolutely you can do.
But the overall charge of the molecule is zero now. Then how can we optimize?
Let me show. I will show the window. Let me share the screen. So you will understand the concept. Are you able to see the screen?
Yes, sir. Yes, sir.
Okay. Thank you. Let me close all the windows. I think you are able to see the screen.
Yes, sir. Yes, sir.
Okay. Suppose we are taking any ion here. Let me draw the structure. You can write structure in this window, or you can also take the structure from the mole file, from the ChemDraw. Let me take first this thing from the ChemDraw. Okay. Let me take a carboxylate anion. Okay.
Okay, sir.
Okay. Save this file. Save as. This is benzoate anion, benzoate ion. Okay. I will save it as a mole file. Okay. Then what you have to do? You have to open that file in the Gaussian. So here I will select the mole file, benzoate ion. So here I will open the file. Okay. So when you will click on here, so what you have to do, first of all, see whether now hydrogen is shown on the oxygen. See in the calculation setup what kind of charge is shown. So I will click on the optimization, then method. Here charge is 0. So what I will do? I will remove the hydrogen from the oxygen through builder. Okay. So what you have to do? You have to select the delete atom. And now we have the charge on oxygen. So what charge is there? Oxygen is having -2 charge, correct? So here in the job type, what you have to do? Again, first you have to select the optimization. Then you have to go to the method. So here, are you able to see the doublet state?
Yes, sir.
Okay. That doublet state is for the charge of this compound. Now it is not singlet. That is showing the charge of that compound. And that charge, it is -2.
Minus. Minus.
Yes. -2.
Okay.
For inorganic compound, it will be -1. Any other question from any other student?
If the cations and anions are along with each other, means the ionic liquid, we can say that the cations and anions are together in a liquid state.
We can draw the structure, and as per the requirement, we can draw the charge.
Okay, sir. Thank you, sir.
You can send me the structure, and definitely I will perform the calculations.
Okay, sir. Thank you.
Any other thing?
मला स्वतःला वाटतं असं कसं झालं.
I think there are no further questions from the participants. Yes, sir. Yes, sir. Yes, sir.
Okay, sir.
Thank you, sir.